In this video, let's go through a different method of involute spur gear design. If you're just tuning in, please see the last video that was put up where we go through using an equation-driven curve to model this, as we're not going to go through everything that was covered in the last video. This video covers more an approximated method of creating the involute profile of a gear tooth, and the approximation is really useful for those who cannot have the capability of generating an equation-driven curve in their CAD platform, or at least not one in a way that would be useful to model this kind of gear. I think that even though the approximated method has some inaccuracy, it is very usable in real life, and in the next video we'll do an analysis as to why I believe that is so we can get some hard numbers to work with. Because it's easy to say, oh yeah, the approximated method is an approximation, so it's not usable, but it's quite another to look at the hard numbers that this method can produce, and when you can and can't use it based on actual objective numbers. So let's go into two additional equations, right? These are the equations that we used in the last video to model our involute gear. And here are two more equations that I think will be useful. Angle alpha, which is the pitch diameter squared, and then we subtract the base diameter squared, and then we square root that, divide by the base diameter, and subtract your pressure angle in radians and not degrees. And then we take our root to root tooth angle, which is 360 divided by 2 times the number of teeth, plus 2 times the alpha value that we just found. So when we start modeling, we'll have a nice visual that I can actually tell you a little bit more about what angle alpha is and how it interacts with the root to root angle. Additionally, you can see since we have alpha here, we can combine these into one larger equation, but that's a bit harder to enter into the platform, and I think a little bit harder to edit if you need to make any changes. So with all that, let's go into the modeling and see how we can actually create a gear with all of this information. So this is the gear that we made in the last video. As you can see, we have an equation-driven curve right here that models our involute profile. So if we start where we left off in the last video, and that's why I say watch the last video if you haven't, let's delete everything. Indeed, you can also download this stuff from GrabCAD. Let's get rid of this sketch as well, and then we can delete our equations. So we're left, thank you, SolidWorks, we're left with all of the equations that we were working with in the last video, and this is probably a good starting point for us in this video. So the first thing that I want to do is the equation for angle alpha calls for pressure angle in radians. Why don't we just run a conversion for that separately? So we're going to call that pressure angle radians, and we're going to say, of course, equals our pressure angle. There it is. And we're going to say times, and we're going from degrees to radians, so that's pi, capital Pi, divided by 180. There we have our radian conversion, and now we can start working on the angle alpha, which I will simply call angle alpha. And this will be in fact, I'm going to open 2 parentheses, or if you're British, I believe they're called brackets. So we're going to take the square root of 2 more parentheses. We want our pitch diameter times our pitch diameter, close parenthesis, subtract, and then we have our base diameter, right? So we go to our global variables, base diameter times our base diameter, and then we'll add another close parenthesis for the close square root function. Then we want to divide by our base diameter again. And then we'll close off that parenthesis, subtract our pressure, and I have to add a quotation there. Subtract our pressure angle in radians. And then it looks like I need another close parenthesis. And there's one little nuanced thing that I haven't done, and since we're working in radians, we want to convert everything back into degrees, and so we're going to say times 180 divided by pi at the end, and that will give us the correct angle alpha. So I have a diametral pitch of 2, 30 teeth, 20 degree angle, and with those inputs we should have an output of 0.853815. Next, let's find our root to root angle. And our root to root angle, in my opinion, is a lot more simple. We'll say 360 divided by 2 times the number of teeth. And I really should have quotes around that. And then we're going to say plus 2 times, and I should have quotes around that, 2 times the angle alpha. Let's add some brackets if you're British, parentheses if you're American, to make the order of operations a little bit more clear. And that's looking right. So we're going to say OK on that, and we can begin modeling the gear. We'll go to the front plane, and I'm going to draw a series of circles of dimensions that I care about. In fact, before anything, I'll highlight all and make sure that these are for construction. And we want the addendum angle, right? This will mark the outer diameter of the gear, or the end of the tooth. And so that'll be our addendum diameter there. Global variables. We could use our base diameter as well. That would be useful. And we'll take our pitch diameter. And our base diameter. Oh, looks like I already put our base diameter in over here, and I think I meant my dedendum diameter. There we go. So we've got our 4 circles. And this time I'm going to start an involute tooth from the base diameter, and it will be tangent to vertical, and we're going to move out this way. Whereas our equation-driven curve put it down here before. Not a big deal. To start that, I'll draw a center line from my origin to my base diameter. And I'm going to mark out an angle here. And I'm going to add an angle between these 2 lines that's going to say equals the number of, I should say our root to root divided by 2. And now I want to make a series of center lines, about 10, that are all coincident onto this circle. Equal 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 equal, right? We want all these to be equal. Good. So I think we're fully defined. We have these equidistant points. Exactly what we want. That did not stick where I wanted it to. So we have our vertical line right here. We have the angled line right here. And we're just making a series of lines on the points that we've made. Okay. Next, we have our circle. We're going to make each of these tangent to our circle. All right. Now, if you recall, an Involute profile from the last video is really made by wrapping a string around something round and then tracing it as you unwrap it. And we can do that with some of these lines. And as you can see, our base circle would be the circle that we would unwrap around to create an Involute profile. So if we can grab the arc length of an arc from here to here, I believe that we can create certain reference points as an Involute profile. So we care about the arc length from here to here. Let's add one more equation, and we can utilize S equals R theta. Now S equals R theta requires angles in radians, and so I think it would be wise just to parse this out separately. We can say, I'm going to call this angle radians, is a very generic name. So our angle radians is going to be global variables. We care about root to root. And then we're going to say divided by 2 times pi divided by 180. All right, so that would be our angle in radians. And then we're going to say, in fact, I can call it arc multiplier. We're going to say global variables, angle radians, times, and then we care about our radius, right? S equals R theta, we have our theta. So we're going to multiply it by our radius to say global variables, base diameter divided by 2. And there we should have the arc length of this arc, right? Because this is our base circle, so our base diameter divided by 2 is the radius. And then the angle between these lines is that root to root divided by 2. And so S equals R theta. Let's go back and edit this sketch. We're going to say global variables and arc multiplier. You're probably wondering why I'm saying multiplier. So this is the second line that traverses 2 angles. So we're going to say arc multiplier times 2, right? Equals arc multiplier times 3 equals arc multiplier times 4, and so on. As you can see, these points start carving out a little involute profile. They fall where the involute profile falls, and we're basically using these line lengths to act almost like a string that will be at the correct length as it unwinds around the base circle. Arc multiplier times 5. All right, so there is an involute profile by points, and we can now examine what strategies we have to make this into an involute profile. I think we are limited to using a spline, and one method would say that we're going to draw a spline to every point and of course we want the tooth to end here, so we'll make this for construction just as a reference and make another spline. Up this way, and then at the very end we'll take the end of the spline, make it coincident, and make it coincident. Great, and then we have the capability of saying, well, this is the center line of my gear, right? Because this is the root to root angle divided by 2, so I have a nice center line. I can mirror the spline across this line and then, sketch in what I want and create the gear that way. Now, if we change the equations in our gears, which this is why we've designed the gear this way, so that we can just type in 3 numbers and the gear defines itself. If we do that, then these angles will move up or down, right? And so this might move down, and then you're like, well, then I've got the spline that isn't connected to this reference point, and so I'm a little bit more limited in my resolution. And so it can become complicated if you adjust your gear and then maybe have to redraw a spline depending on how big of a change that you make. So I'm a little bit less in favor of this method. What I would do is multi-body modeling. However, I do recommend you play around with the sketching method of the splines, as it can be quite helpful to understand how these models update and so on. But instead I'll make this spline a driven feature, and all right, I should say a sketch feature, right? Not a construction feature. I for sure want to make a solid arc from here to here. And we have our circle updated, and we say equal. We'll make this horizontal. And it doesn't really matter how far we make this out, but I like pretty far. Let's go 5. I'm in inches. If you're in millimeters, same thing, right? This should be unit agnostic because gears come in all shapes and sizes. So we have a complete profile, except there's one thing that I would like to fix. You know what? I should actually just get rid of this arc and get rid of this thing. We want this tooth to be a little bit deeper than it is, so we're going to come down here and select this midpoint. There it is. Coincident and horizontal. So our tooth will go deep. And you're probably looking at this thinking, what a strange way to define this. But I hope it'll come a little bit clearer as we go. So we're going to exit our sketch. We will extrude our tooth. Let's go mid-plane on this. And a total distance of, let's say, 2. Excellent. Now we want to cut the tooth. And we have a nice reference in this sketch, and I can show the sketch that we have this line acting as like a midpoint between the tooth. So I will work on making an axis, and I'll use our top and right planes. And so where these planes intersect, the axis is created, and where the axis is created is actually going to be the center that the gear rotates around, because it falls right on our sketch origin. So I create an axis, I'll create a plane on that axis, and then I can specify a point on the midline, and now this plane becomes like a 3D midpoint reference to our tooth. So I'd like to split this tooth. So there is our tooth so far. Let's mirror a body. And now we want our tooth to come to size. So we can hide some of this. I guess the axis is still pretty handy to have. Let's go with sketch on the front plane, and we want to cut the tooth to size, so we'll make this our addendum circle. And then we'll do a cut through all both, and we'll flip side to cut, so we cut the outside of the tooth instead of the inside, and that is a tooth cut to size. We can run a circular pattern on our bodies. We can choose our direction around the axis that we've made. And we want this to equal the number of teeth that we have, so that it will update the number of teeth if we change one of the variables. And then we'll mirror, or pattern rather, our bodies. So there's our geared teeth. Let's do one more sketch on the front plane. And we want this to be our dedendum circle diameter. So global variables, dedendum diameter. Let's add some design intent into this to where if we change a dimension, we don't have to update multiple extrudes. We're going to say up to surface in one direction. We're going to say up to surface in another direction. And we're going to call it good. Now there's a potential error that just occurred, and that is as we change the numbers of teeth, the surfaces that we've referenced on each side may not exist if the teeth are deleted. So if you get a rebuild error, that's probably it. We've referenced a surface of a tooth that no longer exists, and so it can't complete the extrusion or doesn't know how anymore. With that being said, here's a gear. I think I'll edit for mate's sake this sketch, and we'll add in, let's go with a 2-inch. Or if you're in millimeters, just make it 2 millimeters. Hole there. Makes it easy to mate that way with some references. So we should have a fully working gear. Let's see how this works. We're going to manage equations. We're going to say our number of teeth. Let's take it down to 25. And it seems to update nicely. Down to 10. Yep. Let's make this 15, and we'll change the diametral pitch to 3. That looks pretty good. Down to 1. Very nice. Up to 4. Seems like we're working on a wide variety of angles pretty well. We've got almost like internal splines on this one, and I think that's going to be due to how our history came up. So, yep, that's just our boss extrude with our circle diameter that can be updated. So you know what, let's take this back to 2 and 30. And just to confirm that our pressure angle still works, we can make it kind of a weird value of 10, and that seems to update pretty well. 14.5 works well. So there's our typical 20-degree pressure angle. I told you I was going to talk a little bit more about angle alpha, so let's do that now. We're going to make a sketch and allow me to draw a few lines. I also should show this here. We'll go to our center line, here to here, and on this vertex, so what are we doing when we use this angle alpha value? We have some angles here, and our root to root angle says 360 divided by 2 times the number of teeth. If you express that in degrees, that will be the angle from here to here. Alpha is the angle from here to here. And so 2 times alpha would be these two angles combined. And you add that to the first part of the root to root angle equation, that's this angle. So that's how we find the angle of root to root when we go to dimension these teeth. That's what we're figuring out. So this is 360 divided by 2n, and this is the angle alpha. That's a very long equation that we just made. So that is how that works. I'm going to add some alignment features. You know what? Let's do that in the next video. And say insert part. Despite the gears looking pretty dressy, right? This is our perfect curve part, and I can move body. And we'll use the mate settings. So we're concentric there. We'll just align these two here. You can tell it is really hard to tell any difference at all. So in the next video, we're going to kind of analyze this and see what the actual dimensions are different between these gears. So I hope this video was helpful so far. If it was, please subscribe, and I'll see you in the next one.